Okay, we'll get started. First, the administrative thing. The first tutorial is today at 1:30. Please read carefully the information that's on the on-cue page about proctoring and about submission. Okay, just to make sure you understand how that's all going to work. Hopefully, there won't be any problems. Okay, and the Zoom link for the proctoring is on the tutorials link on the on-cue page. So Henry has set that up. Okay. All right. So today we'll finish the example that we started last time, which was the example of the rolling disk, and we kind of done the hard part last time. But I unfortunately have to draw the stupid thing again. Okay. All right, so we had this disk that was rolling on a plane like so. And we had decided that we had a spatial frame that we would put like so with the origin in the plane and two of its basis vectors spanning the plane. And then the body had its body frame. Like so. Okay, and then there was a spin angle, which I think I called theta. And then there was a roll angle, which I think I called phi. It's possible I did those the other way around. It doesn't really matter. And so what we had done last time was we had rotated by a sequence of three simple rotations about the spatial axes. We found a way of rotating the body frame into the spatial frame, and so therefore what we did was we were able to find R. And so what we did last time is we found R of theta and phi. Okay, and it was and you know, I didn't explicitly write the thing out, but it was a product of three matrices, each of which depended in a simple way on theta and phi. And the product isn't that awful. It's just multiplying 3 by 3 matrices is something best done in private. Okay, and so the only thing that remains this time is to find little r. Okay, and so remember we just have a single body here. Okay, and so Q free is just SO3 cross R3, and we found R, and we need to find we found big R, and we need to find little r. Remember that the little r is just the vector from the spatial origin to the body or origin. And if you think about that for a second, it's pretty clear what that's going to be. So it's going to be, you know, that vector there, and so the height, okay, is always going to be the component of little r in the S3 direction is just going to be a constant, and it's going to be the radius of the disk, and then the S1 and S2 components of the vector little r are going to just be arbitrary x's and y's. Okay. All right. So let rho be the radius of the disk. And in that case, R is simply X, Y, row for x, y in R2. Okay. All right. So that sort of finishes this example. But it doesn't finish talking about configuration spaces. So why is that? So here we defined Q as a submanifold. In fact, our specification was that Q should be a submanifold of Q free. Okay. Now, when we talked about configuration spaces back in lecture 1, we didn't do that quite the same way. So let's maybe revisit the examples again, okay, and try and sort of bring the two approaches together. They're equivalent, but it's worth understanding exactly how they're equivalent, okay? And then understanding what the pros and cons are to using the two different kinds of representations that we talked about. And so the first example, remember, was just this planar rigid body. Okay. Now, in lecture 1, we didn't actually do this example, but if we did, we would have said that Q, I have trouble with my Q's on my tablet. Q would be, well, the body can rotate and it can translate. Okay, so we would have said that we have a rotation, and we decided in the first lecture that rotations were measured by, or were represented by the unit circle in the plane across R2. Okay. Now here we have Q. I'm just going to stick to that Q. Is a subset of SO3 cross R3. Okay, and we explicitly described that subset in the previous lecture. Okay. All right. So how are these two things related? Okay, well, they're, if you think about how we represented our subset of SO3 cross R3, there was a theta and an X and a Y there, okay? And that's, kind of what that space is. That's really the space of thetas and X's and Y's. And so really what we have when we wrote this down, right? So we had an explicit representation of Q, okay? And if you look back at that explicit representation, what you're really doing is you're defining a map from this space into that one. Okay, we're defining a mapping from S1 cross R2 into SO3 cross R3. Okay, and this in this example is Q free. Okay, and what is that mapping? Okay, well, what does a point in S1 look like? Well, a point in S1 is a point on the unit circle, right? So it's an X and a Y. Well, we can write, and it's an X and a Y that satisfies X squared plus Y squared is equal to 1. And so we can write any point on the unit circle as cos theta sine theta. okay, for some real number theta. Okay, and then x, y. Okay, and then this maps to, okay, the element of SO3 that we decided on last time was cos theta minus sine theta excuse me. Okay, so that was our big R, and then it was x, y, 0. Okay. Oh, and so that connects the two ways we have of talking about what the configuration manifold is. All right, we have kind of a simpler representation. So you know, this kind of an expression is more compact than this one, and for some examples, this representation is way more compact than the explicit writing of Q as a subset of Q free. Okay, and so this has the benefit of compactness. However, this representation is computationally going to be the one that we're going to use. And so when I tell you to give me Q, okay, you can do this and it won't be wrong, okay, but you're going to have to do this anyway. All right, so you know, I guess I would say you may as well just start out with that. Okay, for reasons that we'll see as we go along. Okay. All right, and then our second example was this, you know, either a double pendulum system or the world's lamest robot, however you prefer. Okay, that's even for a lame robot, that's a feeble looking hand. All right. Okay. And so last time, well, so we did look at this thing in lecture 1, and there we decided that Q was S1 cross S1. Okay. Perfectly natural. Two angles describe the position of this pendulum or robot. Okay. But then when we talked about this yesterday, we said, okay, there's two bodies here. And so the configuration manifold is really a subset of SO3 cross R3, two copies of that. And then we sat and we explicitly calculated what points in this space looked like, which represented the configurations of the robot. So we had two big R's and two little R's, and you know, the elementary in this example. So we wrote those things out. Okay, and just like here, these two representations here are represented by a mapping. The same thing goes here, is that now we're going to connect these two representations of the configuration manifold by a mapping from this one into that one. Okay, and let's explicitly write that thing down. Okay. Okay, so we have a mapping from S, and so this one's going to be long, so maybe move it over here. S1 cross S1 into SO3 cross R3, two copies of that. Okay, and so again, we're going to represent points in S1 just like we did up here as cos theta, sine theta, but now we have two of them. So we're going to have cos theta 1, sine theta 1, cos theta 2, sine theta 2. Okay. And that's going to map into Okay, so it's going to map into SO3 cross R3, 2 copies of that. All right, so it's going to be some big, long thing, but simple. So this is big R1 that we wrote last time. Okay, so this thing is R1. Then we had little r1. Okay. And little r1, remember, looked like L1 over 2 cos theta 1, L1 over 2 sine theta 1, 0. Okay, and so this was little r1. And then we had big R. Oh, sorry, my light went out. Sticky switch. Okay, and then we had big R2, which was the same thing as big R1, with theta 2. Okay, and so that thing is R2. And then finally we had little r2. Okay, and little r2 was L1 cos theta 1 plus L2 over 2 cos theta 2, L1 sine theta 1 plus L2 over 2 sine theta 2, 0. And then, okay, and then this whole business was R2. Okay, and so that's how you connect. And so this is an example, and you know, really, if you were to write down a point in S1 cross S1, you know, you wouldn't sort of, you know, write it like that. You would just kind of say that a point in here looks like theta 1, theta 2. And really what you're doing when you do that is you're representing a point, not in S1 cross S1, but in a coordinate chart for S1 cross S1, and the coordinate chart is defined by the angle coordinates theta 1 and theta 2. Okay, and so you can even take this representation, and when you represent it in coordinates, make it even more compact. Okay, so really you have a mapping which maps theta 1, theta 2 into all of this stuff. Okay, and so you see the advantages of each of, well, you don't see the advantage of this right now, but you will. Okay. All right. So, oh, sorry, we have a, right. So the question is, are these mappings, mappings that I've defined, and since we have this one here, we're talking about this one, let's say. Is that map a diffeomorphism? Well, no, it's not, and it can't be, because what's the dimension of this thing? The dimension of this thing is 2, and the dimension of this thing is 12, right? So 3 times 3, sorry, 3 plus 3 is 6 times 2 is 12. Okay. But you have something in mind that's right, and that is if you take the image of this inside here, okay, so that's going to be, you take the image of this inside here, that's going to be the submanifold Q, okay, and then this mapping is indeed a diffeomorphism from S1 cross S1 onto Q, okay, so that is true, but definitely not onto here, okay. All right. And then we'll look at the third example. And you know, and now there's not very much surprising now. Okay. However, there is one thing that I think we should think about. Okay, now if I had asked you in lecture 1, what was the configuration manifold of this thing? Okay, the configuration space. So, as we had this sequence of examples of sort of increasing difficulty as we went along, we may well have stumbled across S1 cross S1 cross R2. Okay. And why would we have said that? Well, we would have said that because the body, the little disk, spins about the vertical axis and rolls about the axis which is orthogonal to the its plane of motion. Okay. However, you should really not just have believed that. Okay. And why should you have been suspicious about that? Well, you should have been suspicious about that for the same reason that if we had the rigid body fixed at a point, but rotating about all 3 axes by a rationale like I just used here, okay, we would have said that the configuration space for a rigid body fixed at a point was S1 cross S1 cross S1, right? Because it's a rotation about 3 axes, just like this is a rotation about 2 axes, okay? However, for the planar rigid body, that, intuitive guess is wrong, okay? It just so happens for this example that intuitive guess is correct. And so we might have stumbled across this, okay? But back in lecture 1, our reasoning for that would have been a little bit questionable, okay? But now we kind of have enough machinery that we can sort of do this in a precise way. Okay, so we described last time and then finished it earlier on. We described Q as a subset, okay, of SO3 cross R3, okay? And so again, what we do is we establish a mapping from this space into this space, okay? And what's that mapping? Okay, so the mapping is a mapping from S1 cross S1 cross R2 into SO3 cross R3. Okay, and what is that mapping explicitly? Okay, so I'll write it out in sort of full detail. And so, I'll do things properly here, and I'll write a point in S1 like this. Okay, not like this. Although, like I said, when you begin to work with these kinds of things, you stop doing this and you just do that. Okay, but we're not really experts at this yet, so let's be careful. Okay. So, so my 2 S1s correspond to the roll angle and the spin angle, which we had called phi and theta last time. Okay, so it's cos phi, and again, I might have permuted these, but whatever. Okay, so that's my first S1, and then my second S1 is the spin S1, and then X and Y. All right. And the mapping then just maps into, so we had this thing R of theta and phi. Okay, so we had some expression for that. Okay, and then little r was X, Y, and rho. Okay. Now, what do you have? There's some things to do here. Okay, and we're not going to do them because it's a little bit messy. But to really make this make perfect sense, what you need to do, and this is very much related to the question up here about whether this map was a diffeomorphism, and I said no, it's not a diffeomorphism, but it's a diffeomorphism kind of onto its image. Okay, and it's only not a diffeomorphism because the space is too big. Okay, so we have a similar thing going on here. We have this space which maps into this one, and it's not a diffeomorphism, but it has an image, and the image is the set of all things that look like that. Okay, and you have to verify that the mapping from here into here is a diffeomorphism onto its image, and so there's some machinery from differential geometry that you have to go through for doing that. Maybe the first step that you should take is to verify that this mapping is a bijection. Okay, that's sort of step number one. And then kind of once you've done that, then that's sort of the hard part. You need to verify that it's differentiable, but we have concrete expressions for little r and for big R, so differentiability is easily verified. And then you have to kind of by the rules of what it means to be a diffeomorphism, what you need to do is you need to take the inverse. Okay, so you take the image inside here, and then you construct a map which goes backwards like this, and then you need to show that that's also smooth. But it actually turns out there's slicker ways of doing that, but that requires just getting into a little bit more stuff about differential geometry than we need. Okay, and so I will summarize that long discussion by saying fact. This mapping is a C infinity diffeomorphism onto its image. Okay, and it's not a hard fact to verify, but we just need a little bit more stuff than we have in our toolbox right now. Or in fact, that we will have at the end of the course. Okay, all right, so there's the end of configuration spaces, all right? So the next topic is going to be more physics, okay? So we're gonna have a little tiny bit of physics, and then we're gonna launch off into a fairly long section about mathematics, okay? Then so there's going to be some new definitions from differential geometry. Then we're going to have a pile of linear algebra, which is not going to be really new to you, but it's going to be new notation for talking about things in linear algebra, and sort of focusing on sort of carefully on elementary things that you already know about, but thinking maybe a little bit more hard about them than you did back in 212 or whatever linear algebra course you took. Okay. Okay, so first, a little bit of elementary physics. Okay, so we have a particle moving in R3. And so what does that mean? Well, we do what we always do. We have a spatial frame. Our little particle is there, and then we have a vector R, which just has some components, let's say X, Y, Z, with respect to the frame S1, S2, S3. Okay, and then the velocity of the particle is R dot. Okay, and so so let me sort of be a little bit more. The velocity of the particle as it, because I have no time in here yet, so as it follows a path prescribed by R as a function of time is simply the normal time derivative. Okay, so nothing exotic about that. Okay. But things are different if I have a rigid body, okay. Right, so here's my rigid body, and as we have done, it carries with it a body frame. Okay, and then we have an associated R big R and little r that describes the position of that body. Okay, so it's translational position little r, and then it's kind of rotational position big R. If the body moves, okay, so what does this mean? So this means that it follows some path. So in SO3 cross R3. So it's going to be big R of t and little r of t. Okay. And the question that we want to think about is, sorry, I should say question since we use Q for other stuff. Okay, well, naively, you would just say it's big R dot, little r dot. Okay, and I don't know, that may be fine. As we'll see, big R dot is not a super good physical representation of velocity, just on the grounds of physics for the body. So that's one defect of that kind of a setup. And another defect is, what is big R dot? So I know that R is in SO3, and so capital R of t is going to be some kind of a curve in SO3 parameterized by time. Here, if my particle's moving, I kind of just think of the velocity as being R dot. Okay, what's big R dot? Either physically or mathematically. Okay. And so these are the physical questions that we want to try to understand here. Okay. All right. And so to do this requires some new mathematics. Well, mathematics connected to manifolds, which we've already talked about. Okay. All right. And so the problem is this. The problem is that if I have a manifold, okay, so my way of thinking of a manifold is that I have a thing that looks like this. And let's say I have some curve on here. Okay, and so a curve is a mapping gamma. So let me make that look a little bit more like a human gamma. Oops, please go away. All right. And so this is, so at a point, let's say gamma of t, I kind of want to say what's gamma dot of t. And, intuitively you have a picture of what that is. It's kind of a tangent vector, like I drew it there, okay? Now the problem is that, what is that thing actually? Okay, up here when we talked about the body, the velocity of a particle, we knew what r dot was, right? It's x dot, y dot, z dot, and we know what dot means. It means d by dt. Okay, and that's just because we're in Euclidean space and we know how to take derivatives in Euclidean space in a meaningful way. We don't know how to do that on a manifold, or at least we don't know how to do it until I tell you how to do it. Okay. Okay, now the only way we have of understanding what that might look like is if we represent this thing in coordinates. Okay, and so I would choose a coordinate chart. Let's say u phi. Okay, and so I have phi of u down here, and then my curve, sort of goes like this down here, and now down here it makes perfect sense to say what this means, because now I'm in Euclidean space, right? And so I can take the derivative of this thing at this point, and it makes perfect sense. Okay, and so that's going to be how we get at what velocity is, and velocity in this geometric setting is what we're going to call a tangent vector. Okay, so with all that as kind of motivation, let's just give the definition. Yeah. Okay, so if I take a point x in M, I want to talk about a curve at x. It's a simple thing. Okay, and so I'm going to have a differentiable mapping. So I here is going to be an interval. And I'm going to require that gamma, so let me say it this way, okay, is an interval with 0 in the interior of I. Okay, so I can't be, let's say, the interval 0, 1. Okay, the closed interval 0, 1. 0 has to be in the interior of the interval. Okay, so I is an interval with 0 in its interior, and gamma of 0 is equal to x. Okay, so notice that everything here makes sense. Okay, and that's kind of important. And what do I mean by that? What might not make sense here? What may not make sense is that, right? Okay, but it does make sense because we've talked about what it means for mappings to be differentiable. Okay, so I is an interval, so I is a subset of R, and because 0 is an interior, we may as well take I to be open. Okay, so I is an open subset of R, so I is a manifold, right? Open subsets of Euclidean space are manifolds. M is a manifold, and we've talked about what it means for mappings between manifolds to be differentiable. All right, so everything in this definition makes sense with what we know so far. Okay, so that's a simple concept. So the idea is it's just a curve that is defined at 0, okay, and not just at 0, but around 0, and at time 0, it passes through x. Okay. Two curves at x, let's say gamma 1 and gamma 2. Okay, and they need not be defined on the same interval. It doesn't really matter as long as they have 0 in their interior. Okay, so two curves, gamma 1 and gamma 2 at x are equivalent. If for any chart u phi about x, okay, so that means x is in u, of course. We have d, okay, so d here is going to, first I'll write it down, I'll tell you what all the symbols mean. Sorry. If that's true, okay? So d here is the normal derivative for mappings between Euclidean space, the thing which in 280 you called the Jacobian. Okay, and and so the Jacobian is defined again for mappings between Euclidean space, and so we're, if you just think about what's going on here, each of these are maps between Euclidean space, but we're going to spend some time just explaining exactly how to think about this condition, and then you'll kind of see what it means. Okay, so here's the picture that's attached to that. All right, so I have my manifold M. Okay, and I have two curves. I have gamma 1 and gamma 2, okay, defined on some intervals with 0 in their interior. Okay, so here's my point x. All right, so I know that both of these curves pass through x at time 0. Okay, so x is gamma 1 of 0, and it's also gamma 2 of 0. Okay. All right, so let me draw my curves. Okay, so let's say that gamma 1 looks like that, and let's say that gamma 2 looks like that. Okay, and I've drawn them so that they appear to have the same tangent vector at x, because that's actually what I'm trying to define. Okay, so this is the curve gamma 2, and this is the curve gamma 1. Okay, now I choose a chart. Okay, so I put a U around there with a chart map phi. Okay, which maps me down into Euclidean space. Okay, so now what are these things? Okay, well, these things are obtained by just going gamma 1 and then following it with phi, and then gamma 2 and following it with phi. Okay, and so phi composed with gamma 1 is a mapping like this, and phi composed with gamma 2 is a mapping like this. Okay, and so if this is my point phi of x, okay, then I have these curves, and these curves now are just curves in Euclidean space, and they pass through here like this. Okay, so let's say that this is the curve phi composed with gamma 2, and that this is the curve phi composed with gamma 1. Okay, all right. Good, so that kind of is the picture of how everything fits together. Now, what does this condition look like? Okay, well, this says so I have these mappings between Euclidean space, right? So it goes from R1 into Rn. Okay, so I have phi composed with gamma 1, and then phi composed with gamma 2, and then I take their derivatives and I evaluate them at 0. Okay, so when you talked about 280 in vector calculus, one of the ways that you think about the Jacobian is you think about it as being a linear map. Okay, and what will the linear map here be? The linear map here will be between R1 and Rn, okay, because the map is a map from our interval in R1 to Rn, and so the derivative will be a linear map from R1 into Rn, okay? Which, if you think about the shape of that vector, that's going to be a column vector, right? And so I'm going to take that derivative and I'm going to now evaluate it on, it's a linear map from R into Rn. I'm going to evaluate it on 1. Okay, so in other words, I'm going to kind of take these things and I'm going to invisibly multiply them by 1. Okay, and so when I do that, what do I get? Well, I get a vector in Rn, and that's the velocity, right? Okay, and so that thing, and so now this thing down here, this has actual precise meaning, right? It's just exactly this, and the definition is that it's also that. Okay, so the two things are equal. So this is d of phi composed with gamma 1 of 0 equals d of phi composed with gamma 2 of 0. Okay. And so the definition of equivalence is of curves just means that when you represent the curves in Euclidean space in coordinates like so, okay, that they have the same tangent vector at 0. Okay, so that's, if it's the kind of a definition that if somebody forced you to make the definition, that's the one that you would probably make after you thought about it for a little while. Okay. Okay, so and then a final definition, or let me see how far I get here. Okay, so now we have this notion of equivalence, all right? And I'm going to use that notion of equivalence to define a new thing, which is kind of the thing up here, okay, which is a tangent vector in the manifold. Okay, so a tangent vector at x is an equivalence class of curves at x. Okay, and of course, it's this notion of equivalence that I'm talking about. Okay, so this seems, way more obtuse than it needs to be, but it's not actually. So it's at the same time extremely simple and extremely complicated. It's extremely simple because if you want to represent an equivalence class, okay, then what do? Well, you choose a single member of the equivalence class. And what's the equivalence class? Well, it's an equivalence class of curves at x. And so to represent a tangent vector, all you really need to do is you need to take a single curve that passes through x, let's say gamma 2 in this picture here, okay, and then consider all curves which, when they pass through x, have the same velocity when I write it in coordinates. Okay, so to concretely represent a tangent vector means taking a single curve which has in coordinates a specified velocity, and then abstractly the tangent vector is all curves which pass through x with that same tangent vector in coordinates. All right. All right, so that's what a tangent vector is. The tangent space at x Okay, and this thing's denoted by TXM is the set of all tangent vectors at X. Okay, so that's a pretty clear definition. And so, okay, so you choose a curve that gives you an equivalence class of curves. Then, you choose some other curve. Okay, and that's going to have its own equivalence class. And the set of all such things is the tangent space. Okay, so it's the set of all equivalence classes of all curves at X. And final piece of terminology. Is the union of all the tangent spaces. Okay, so I just barfed out a bunch of definitions there at the end. We're going to spend a significant amount of time talking about these, but these are the things that we're going to spend the next little while talking about. Okay, so that ends the lecture, and so I will stop the recording.